Welcome to our tutorial on dynamic light scattering and zeta potential analysis. Throughout this guide, we'll explore the fundamental principles, operational techniques, applications, and constraints of these methodologies. Dynamic light scattering is a technique that non-invasively measures the size distribution of particles suspended in solution. It leverages the concept of Brownian motion, which is the random movement of particles due to collisions with solvent molecules. DLS examines fluctuations in light intensity scattered by these moving particles, providing critical information about their hydrodynamic diameter and the range of sizes within the particle population, known as polydispersity. In dynamic light scattering, the diffusion rates of particles are crucial for determining their size. Smaller particles diffuse faster, while larger particles diffuse more slowly. The rate of this diffusion, or Brownian motion, is quantified by the translational diffusion coefficient. We measure diffusion rates by illuminating the particles with a laser. If these particles were immobile, the intensity of the scattered light would remain constant. However, in reality, as particles move and diffuse, the scattered light's intensity varies over time. This scattering from many randomly moving particles creates a fluctuating light intensity signal. The frequency and amplitude of these fluctuations are directly related to the diffusion rate of particles. The smaller the particle, the faster and more frequently its light scattering fluctuates. To determine particle size, we observe the scattered light signal over time. By comparing the intensity of scattered light at one moment with that at another, we can track how the signal changes. When comparing signals taken nanoseconds or microseconds apart, they appear very similar. However, as the interval increases, the similarity decreases until it eventually disappears, a process known as autocorrelation. By analyzing the autocorrelation function, we obtain the translational diffusion coefficient. Using the Stokes-Einstein equation, which relates this coefficient to the particle size and factors in the solvent's viscosity and the system's temperature, we can accurately determine the size of the particles. This process effectively translates the dynamic fluctuations of scattered light into precise particle size measurements. Dynamic light scattering has a broad range of applications across different fields. Assessment of stability and aggregation tendencies of colloidal dispersions. Study of protein-to-protein interactions, biomolecular complexes, and self-assembled structures. And lastly, the quality control and optimization of pharmaceutical formulations, cosmetics, and food products. To turn on the machine, press the button at the back of the machine and turn on the computer screen. For the measurement, you'll be using special cuvettes that are UV transparent disposable cuvettes. Fill in the cuvette with around 1 milliliter of your sample and then put it in the machine. To set up the parameters for the measurement, first press on the Zetasizer software. Now the window will appear and next choose File, New and Measurement File to create a new file for your measurement. Give it a name and the new empty measurement file will open up. To set up the parameters, you can either choose File, Open, and SOP, and choose SOP Template. This is where you can adjust the properties such as material, dispensant, and parameters of the measurement, such as how many measurements you would like to take. Remember to save the file at the end. To choose the SOP file with the parameters you just adjusted, choose Browse for SOP located at the top of the screen. Once you select the correct SOP, it is time to start the measurement. During the measurement in the Multi-View tab, you will be able to see 3 screens: the size distribution curve, the count rate over time, and the correlation function that tells you how reliable the data is. Once the measurement has started, you will see the records view with the details of the measurement.
Remember to take out the sample at the end of the measurement.
Now we will move to the segment on zeta potential measurement. Using the same equipment as for dynamic light scattering, we can also perform zeta potential analysis. This technique offers an indirect measurement of the net charge present on the surface of the nanoparticles. When charged nanoparticles are suspended in a liquid, they attract ions of the opposite charge close to their surface, forming a tightly bound layer known as the Stern layer. This layer in turn induces the formation of a more loosely associated layer of ions, referred to as the diffusive layer. Together these form what is known as the electric double layer. As the nanoparticles move in the liquid, whether due to gravity, kinetic energy, or an applied electrical field, a distinct boundary forms between the ions that move with the nanoparticle and those that remain in the surrounding medium. The electrostatic potential measured at this boundary is known as the zeta potential. There are a few limitations of the zeta potential measurement. First of all, overly concentrated dispersions can lead to multiple scattering phenomena. Zeta potential measurements are most effective for particles smaller than 5 microns. The medium must have sufficient conductivity to allow for the application of an electric field without causing electrode polarization. And lastly, the zeta potential is influenced by both the nanoparticles and their environmental conditions, including pH and medium conductivity.
The cuvette for the zeta potential has 2 entrances at the top and the electrodes on the side. To fill the cuvette with your sample, you should use a small syringe filled up with around 0.7 milliliters of your sample and ensure there is no bubbles in the syringe. Then, take out the lids that close the cuvette, turn the cuvette around and insert the sample until it reaches the bottom of the cuvette. Turn it around again, the right side up, and insert the additional volume of the sample. It is important that the sample touches the electrodes on both sides of the cuvette. Put the lids on the cuvette without closing it airtight and insert the cuvette, making sure that the ears are facing you.
To measure the zeta potential, you can select Surface Zeta Potential at the top of the screen. And here you'll be able to see the summary of the zeta potential measurements. It is important to adjust the SOP file, and therefore you can select File, New, and SOP. Once a new SOP file opens, you can select zeta potential with the right click on Sample. It is important that in Cell, you change the cell type to the one used for zeta potential measurements, which is the DTS1070. Next, in the measurements, you can adjust measurement duration, number of measurements, and delay between measurements. It is advised to have 300 seconds delay to avoid excessive heat production that may damage the sample or the cuvette. In the advanced settings, you may adjust the attenuation and voltage, or you can keep it as automatic. Lastly, remember to save the new SOP file created specifically for the zeta potential measurements. After you created the SOP files, you may always go back to them and reuse them for future experiments. After you save the new SOP file, make sure you select it in the top bar and press play.
Remember to take out the sample at the end of the measurement.
In conclusion, this tutorial has equipped you with the fundamental knowledge to effectively utilize dynamic light scattering and zeta potential analysis. Happy experiments!